Hi, my name is Dave Reiber, Senior Reliability Leader at Reliability Web. Now we'll continue with RCD, Reliability Center Design, in the domain of Reliability Engineering Management. Introduction. Many industry experts report that the majority of failures, i.e. defects, during an asset's operational phase are the result of poor or inadequate design. Many times, design omissions are caused by inefficient funds or budget constraints imposed due to a lack of understanding of the consequences on the lifecycle costs of the asset. The capital project manager's and designer's performance is judged on how they met budget and schedule targets, not on long-term asset performance, including lifecycle costs. A well-designed, built and installed asset should have fewer failures and a much lower total cost of ownership during the entire life of the asset. Leading and highly reliable organizations integrate Reliability Center Design, or RCD, principles into all aspects of their capital project process, including asset concept, design, development, build, and the install phase. Key terms and definitions. Something that has potential or actual value to an organization. Actual asset design specifications, translation of customer requirements into a comprehensive, detailed functional performance or design specification used to build a particular asset. Asset lifecycle, stages or phases involved in the management of an asset during its life. These phases include concept, design, and develop, build, install, and commission, operations, maintenance, decommissioning, and disposal. Asset lifecycle cost. The total cost incurred during an asset's life, including design and development, build, installation, and commissioning, operations and maintenance, and disposal costs. Availability. The probability of an asset is capable of performing its intended function satisfactorily when needed in a stated environment, a function of reliability and maintainability. Capital project. Projects that include new construction, major repairs, or improvement where the cost is capitalized rather than expensed. Failure. The inability of an asset to perform its design function. Maintainability. The ease and speed in which a maintenance activity can be carried out on an asset, a function of asset design measured by mean time to repair. Reliability. The probability that an asset, item, or system will perform its required functions satisfactorily under specific conditions within a certain time period. Reliability block diagram, or RBD. A diagram showing logical connections among a system's components, parts, and assets. The system is usually made of several components and parts, which may be in a series, parallel, or a combination configuration to provide the designed inherent reliability. Sustainability. The ability to maintain a certain status or process in existing systems, in general, refers to the property of being sustainable, capacity to endure. Principles of reliability center design. Major causes of asset failure are rooted in inadequate or improper design, lack of maintenance, or its improper usage. Human errors involving the skills of the users in operating and maintaining the asset also play a key part. Many failures caused by human error can be minimized by a better design. Inadequate design is caused by the use of unreliable components when building the asset, resulting in high failure rates that lead to higher operations and maintenance costs and reduced useful life. A properly designed asset is made with reliable components, ensuring reduced failures, increased asset useful life, safe, sustainable operations, and reduced total cost of operation or of ownership. The 10 times rule. Design errors or omissions create a higher number of asset failures that cause extensive repairs. The earlier these errors are caught during the design, build, or installation phase, the lower the cost would be for corrective action. It has been found that corrective action costs increase by a factor of 10 in each successive stage. Therefore, it is much more cost-effective to find errors or defects during design, which will result in fewer failures later in the operational phase. You could use a tool such as failure mode and effects analysis, or FMEA, during design to identify these potential failures and correct them either by redesign or the use of reliable and quality components. Designing for RAMs S2. Many design errors, along with commissioning, operations, and maintenance errors, cause failures early in the asset's operating life. These are characterized as infant mortality failures. Other defects and errors that do not appear during asset infancy will eventually surface and cause failures later during its operating life. The preferred terminology for these errors is defects, because that is the consequence of a mistake. But the truth is, an early inaction or wrong action results in a defect that is really a consequence. Another truth is, most of the time, most things go right. Failure is not a normal occurrence. The problem with failures is not the failure itself, it is the consequences resulting from these failures. When these consequences are severe, you want to do everything possible to never let that happen again, or find ways to mitigate a consequence to alleviate its possibility of occurrence. The best way to eliminate or minimize these effects is by designing them out at the source itself and designing them right. During design, you should be thinking about all aspects of reliability, availability, maintainability, safety, and sustainability. RAMS 2. There is a real possibility that a right design or a design done well will cost only a little more but will reduce the total cost of ownership during the life cycle of the asset. You want assets to be reliable, that is, dependable and available when you need them to meet your customer needs. Truly, you want your assets to be designed for high availability because availability is a function of reliability and maintainability. Availability is defined as availability equals mean time between failure divided by mean time between failure plus mean time to repair, or uptime divided by uptime plus downtime. Where mean time between failure is a measure of reliability and mean time to repair of maintainability. Mean time between failure equals mean time between failures, MTTR, mean time to repair. So to have higher availability, you need to design assets with highly reliable components, high MTBF, low failure rate, and low MTTR, low repair time. Reliability and maintainability are design attributes. This means they are best achieved when they are designed to get higher availability. Also, to support safety and sustainability, the design should select components that are energy efficient, use less environmentally hazardous materials, and safe to operate. Your design should incorporate high, reliable components and parts with a high mean time between failures. Use redundancy where needed to achieve desired reliability, ease of operations to minimize repair time, design and condition monitoring and diagnostics to facilitate repairs, minimize use of special tools, use total productive maintenance, TPM, operator-driven reliability, ODR, and 5S principles to optimize design, ease of adjustment to belts and chains, oil filtering, and lubrication. Labeling of piping, hoses, devices, etc. for efficient operation. Required availability by balancing reliability and maintainability requirements. Safe and ergonomic design features to eliminate or minimize accidents and injuries to the personnel and the asset itself. Environmentally clean and energy efficient components and material. Extensive use of standard components including control devices such as programmable logic controllers, PLCs, data needed to measure asset performance, and the process design of how it will be collected. Use a standardized methodology for asset and component hierarchies and taxonomy, i.e. naming structures. Another area in RAMS 2 to consider is mechanical integrity. Mechanical integrity, also known as asset integrity management or AIM, refers to the management of all processing equipment in an organization to ensure they are sound and operating within the realms of safety. Equipment such as tanks, pressure valves, piping, etc. are key assets in the process industry and need to be fit for service all the time since they operate continuously 24/7. Any failures such as leaks, overpressure, or corrosion in these systems can be very dangerous and costly. They need to be designed and maintained with special care, meeting all applicable standards of the Occupational Safety and Health Administration, or OSHA, 1910.119, American Petroleum Institute, API 580, 581, etc. Practices and tools for RCD. Here are some examples of good practices and tools to support RAMS 2 based design. Voice of the customer, house of quality. Voice of customer, voice of quality, also called the house of quality, is a management approach to basic design based on quality function deployment, or QFD. The house of quality has been used successfully by Japanese manufacturers and producers globally of consumer electronics, home appliances, clothing, integrated circuits, rubber construction equipment, and automobiles. This design approach has been used successfully in consumer products, but also can be used for the design of industrial products and assets. The foundation of the house of quality is the belief that products should be designed to reflect customers' desires and tastes. So marketing people, design engineers, and manufacturing staff must work closely together from time a product is conceived. House of quality is a diagram resembling a house used for defining the relationship between customer desires and the product or asset capabilities. It utilizes a planning matrix to relate what the customer needs and how that product is going to meet those needs. It looks like a house with a correlation matrix as its roof. Customer wants versus product features as the main part, competitor evaluation as the porch, etc. House of quality is a very powerful tool as it incorporates customer needs into design parameters so the final product or asset will be better designed to meet the customer or owner's expectations. Design FMEA to mitigate failures. Design failure modes and effects analysis, or DFMEA, is a method for evaluating a design for reliability, robustness against potential failures. It's a specific failure mode and effects analysis, FMEA method, for identifying possible failures during the design phase of a product, asset, or service. Failure mode means the ways or modes in which something might fail. Failures are any errors or defects, especially ones that affect asset performance, and can be potential or actual effects analysis, refers to studying the consequences of those failures. Failures are prioritized according to how serious their consequences are, how frequently they occur, and how easily they can be detected. The purpose of FMEA is to take action to eliminate or reduce failures, starting with the high priority ones. Failure modes and effects analysis also documents current knowledge and actions about the risks of failure for use in continuous improvement. FMEA is used during design to prevent failures. Later, it's used for control, before and during ongoing operation of the asset or process. Ideally, FMEA begins during the earliest conceptual stages of design and continues throughout the life of an asset or service. The DFMEA process is normally employed when an asset, service, or process is being designed or redesigned, maybe after a QFD. An existing asset, service, or process is being applied in a new way. Before developing control plans for the new or modified asset or process, improvement goals are planned for an existing asset or service. Analyzing failures of an existing asset or service, periodically throughout the life of an asset or service. Design for manufacturing and assembly, DFMA. Design for manufacturing and design for assembly have some common attributes. Nowadays, DFM and DFA are commonly referred to as a single process called Design for Manufacturing and Assembly, DFMA. The goal is to design the asset so it is easily and economically manufactured and assembled. The importance of redesigning or of designing for manufacturing is underlined by the fact that 70% of manufacturing costs of an asset, i.e. cost of materials, processing, and assembly, are determined by design decisions with production decisions such as process planning or machine tool selection. Responsible for only 20% as reported in literature such as Computer-Aided Manufacturing, 2nd edition by Ten-Shin Chang, Richard A. Weisk, and Xiu-Pin Wang. The following are key guidelines for good DFMA. Number 1, minimize the number of components. Number 2, use standard commercially available components. Number 3, use modular design. Number 4, design parts with tolerances that are within current process capabilities. Number 5, design for ease of part fabrication. Number 6, design for ease of assembly. Number 7, minimize use of flexible components. Number 8, eliminate or reduce adjustment requirements. Number 9, ease of handling and shipping. Design for reliability and allocation methodologies. The reliability allocation methodology establishes the hierarchy of design requirements about reliability goals. The purpose is to distribute the operational reliability goals from a top system level to subsystems, subassemblies, and components, and then design or select components accordingly. Allocation starts with the asset system goal. For example, the requirement for an assembled machine asset are to design and build a machine with these reliability requirements. Operating hours equals 300 hours per month. Reliability equals 90%. These requirements are translated to mean time between failure divided by failure rates and are assigned to subassembly and component levels. Then each component is designed or selected to meet those requirements. Reliability divided by availability modeling, or RBD. Reliability block diagram is another tool that can be used to find gaps to optimize design from a reliability and availability perspective. RBD is a pictorial representation of the logical interdependencies, also called component configurations, with either parallel or series paths required for the asset, machine under analysis to function correctly. Then, estimated MTBF and MTTR data based on selected components are inputted into the model to get the predicted reliability availability. Several software packages are available that can perform RBD analysis with minimum training, what every reliability leader should know. Reliability, maintainability, and availability, safety, and sustainability are design attributes and should be addressed during capital project execution. Applying practices and tools such as design, FMEA, DFMA, RBD, etc. will optimize design. A well-designed built and installed asset will have less failures and much lower TCO during the entire life of the asset. Summary: things, products, or assets fail in service, but everyone witnessed in the various failure of the products in early daily life. To be very reliable, products must be robust and adequately designed to avoid failure modes, even in the presence of a broad range of conditions, including harsh environments, changing operational demands, and internal deterioration due to wear and fatigue. Designers and engineers should use a combination of practices and tools to eliminate or minimize failure, to enhance design, which will result in reduced TCO. Some examples of these practices and tools are voice of the customer, stakeholders, specifically operators, maintainers, etc., to understand the requirements and the issues. DFMEA and FMEA types of tools to identify failure modes and mitigate their consequences. Design based on RAMS 2 principles. Use of reliable components based on reliability analysis. Use of energy efficient and environmentally safe. Use of modular and standardized components, making design easy to operate, maintain, and ergonomically safe. Considering the use of condition monitoring diagnostics, devices, and display data or dashboards to support operations and maintenance, O&M, in design. Manufacturing and subassembly and assembly of design. Ensure design is easy, economical, and safe to manufacture, assemble, and ship. Finally, the design should not be based on the lowest cost, but on the optimum cost to reduce the lowest cost of ownership.